The topic of this video is multivariable calculus. We'll introduce the topic by introducing multivariable functions. Functions that we've been working with so far have been functions of a single variable. So f of x is x squared, y is equal to ln of x, are both examples of functions of one independent variable, and that variable is x. Sometimes we use a t to denote the variable, and sometimes other letters. Inside this writing of the function, I'll pick on the second one, y equals ln of x, what we're stating here is that y is dependent on the x value. It's not an independent variable. So we can't choose anything we want for y. We choose what we want for x, as long as it fits in the domain, and then that choice will dictate the corresponding y value for a particular function. So what we mean when we say a function of several variables, or a function of more than one variable, is a function where we have a choice for more than one thing, where we can choose the x value and we can choose the y value. So one example of such a function is this one, a function of x comma y, so two variables explicitly denoted, is equal to x squared plus y squared. Functions of this form are three-dimensional. The output of this would be like a height, like a z value, so a z value going up and down. X and y would be values that are in the page, so going forwards and backwards or going left and right. It may sound weird, we have these 3D functions, sounds super complicated, but it's not. You've been doing this for a long time. For example, anytime you talked about the area of a rectangle is length times width, that's a multivariable function. It's a function of the length and the width. We could write this as a of length comma width, a of L comma W is length times width, L times W. Simple function, multivariable. Here's another function with two variables. It's a volume of a cylinder, pi r squared times the height of the cylinder. Pi r squared gives you the area of the circle, and h is the height of that cylinder. Another one with three variables, super complicated, right? Three variable function must be horrendously complicated. Notice the volume of a box, length times width times height. Once in a while, different letters are used, but generally speaking, the output of a function of two variables is said to be a z value. So our 3D coordinate system has our x-axis and our y-axis in the page. So x-axis going left and right, y-axis going from backwards to forwards, so going from the bottom of the page to the top of the page, and then the z value is going out of the page, like off the table, above you and below. So here's a few examples of multivariable functions that don't correspond to things like area of a box or volume of a box. F of x is x squared plus y squared corresponds to something else. It's not a circle. That would be if y was dependent on x and we had something like x squared plus y squared is equal to 4, which would be a circle of radius 2. But x squared plus y squared, being the function f of x comma y, is actually a 3D parabola. It's like a bowl, 3D bowl. Looks like a parabola off on any side that you view it from, as long as you're viewing it from the side, like not from above, not at an angle. Another function below it, g of x is 2 over x minus y. Looks pretty neat. It should remind you a little bit of 2 over x or 1 over x. Square root function, this is interesting. I'll save you from the geometric interpretation of this, but if you want to think about domain, that is a useful picture, or that is a useful concept to have in your mind when you try to picture this function, or what are the x values and y values that you are permitted to plug in. And that will tell you a little bit what the graph looks like. Just part of what the picture looks like. And the last one, ln of x times y. So the only thing to take away from this is that if you combine x and y as independent variables into a new function, the output is going to give you a z value. It'll give you a height out of the page. And that a large number of functions can be constructed from one variable, and an even larger set of functions can be constructed from two variables. Domain is kind of like in very, very general ways a part of this course. For example, knowing that you can't plug a negative number into a log function, knowing that you cannot plug a negative number into a square root function, and knowing that you cannot divide by 0. That's it in terms of the knowledge of domain that you would need. But if you're interested to see how the concept of domain is extended to multivariable functions, I've put some stuff at the back of the notes. I won't go through it in video format. I'm just going to leave it in printed format because it's not really part of the course. But I invite you to have a look at that. It's kind of neat. What do we do with multivariable functions? The first thing we're going to do with them is we're going to evaluate them. We're going to plug in numbers. This function, f of x comma y, is defined as 2x squared minus y squared. And it is important in the definition of the function itself to keep track of which letter appears first. X appearing first and y appearing for a second isn't unusual. It's kind of what we expect to see. But you got to be careful when looking also at the function itself, because the y part of the function may appear before the x part of the function. Say we have 2y cubed minus x to the power of 2. Say that's our function instead. When you're plugging in numbers, make sure you're plugging the right number into the right spot. So in f of 2 comma 1, you're not replacing the first letter in the function with 2, you're replacing x with 2. So just watch for that. It's a common mistake to make. So let's do the first evaluation, f of 2 comma 1. We have 2 times 2 squared, replacing the x with a 2, minus 1 squared, replacing the y with a 1. Now we simplify. 2 times 4, 8, minus 1 times 1, 1. 8 minus 1, we get 7 as the output. So 7 would be the height, the z value of that function at that xy coordinate. If we swap it, 1 comma 2, if we interchange which variable gets which value, now we'll have 2 times 1 squared minus 2 squared. So we'll have 2 times 1 minus 2 squared. So 2 minus 4, negative 2. So that's our z value there, a negative height. So that's below the page. That's below your desk. 7 is above your desk. 0 comma negative 3. So 2 times 0 squared minus negative 3 squared. We have 2 times 0, which is 0, and minus negative 3 squared. Negative 3 squared is positive 9, so 0 subtract 9, negative 9. The last one, we'll swap which one goes where. So 2 times negative 3 squared minus 0 squared. So we'll have 2 times positive 9 minus 0, we have 18. So not much different than just evaluating a single variable function. It's just you have to plug in 2 numbers instead of plugging in 1 number. We'll kick it up a notch in difficulty. This time our multivariable function is a log function. We have a log, or natural log, ln of y over x, plus x squared divided by y, and we want to evaluate it at 2 different coordinates, at 1 comma 1 and at 3e comma 3e cubed. So 1 comma 1, can't really screw it up. We're replacing each of the variables with 1. So we have ln of 1 plus 1. Ln of 1 is 0, so 0 plus 1, we get 1 as our answer. Now the next one will be a little bit tougher. Make sure we put the right number in the right spot. So I'm replacing the y with the second number inside that bracket of the expression, replacing y with 3e to the power of 3. And then replacing the x by the first number in the expression, 3e. And then plus, now x squared, so 3e all squared, divided by y, 3e cubed. And we'll simplify. We have the ln, the 3's cancel. We have e to the 3 divided by e to the 1. Those exponents subtract. We'll get e to the power of 2. Oh, my brackets match in size. Now the next one, we have 3e all squared, which using exponent laws is the first term squared times the second term squared. So we'll have 9e squared divided by 3e cubed. The first piece there, we can use the cancellation law. Log base e of something is just the something. So just the power 2 is going to survive. And from the second part, 9 over 3 is 3. And then we have over e. E squared on top, e cubed on the bottom, one surviving term down below. So that's one way we could write the final answer. Okay, now three variables. This is where we stop trying to make a picture. I mean, we could have went back and made a picture of this thing and made a picture of this thing. I'll show you how to do that later. But for three independent variables, we are plugging in an x value, a y value, and a z value. So the output can't be a z value. It's one of the inputs. Instead, the output is what comes after a z. Well, it's whatever letter you want to give to the fourth dimension. Can we graph the fourth dimension? That depends who you ask, and depends what you count as a graph. Like, would you be okay if we were to use colors for the values, going from, let's say, red to ultraviolet to violet? Would that be okay with you? I don't know. Maybe some people would like that, but I think a lot of people get weirded out. So we're not going to be graphing in 4D or 5D or 6D or however many dimensions we're working with. We won't technically even be graphing in 3D. So we'll just leave it algebraic. We'll leave it as our functions are defined in terms of the letters. Yes, there's always a graph that will correspond to that function, but we're not going to worry about what that graph would look like. So for this question, for this function, we're concerning ourselves with the evaluation of it at different x, y, z triples, at different coordinates. When we're plugging in, we have to make sure we're plugging in correctly. The order matters. It's x and then y and then z. So for this f of 284, x is being replaced by 2, y is being replaced by 8, z is being replaced by 4. So when we do that, we're going to have 2e to the 4 divided by 8, which is 2e to the power 1/2, which is 2 times the square root of e. Next one, 630. So we have 6 times e to the 0 divided by 3. 0 divided by 3 is just 0. So 6e to the 0. Anything to the power of 0 is 1. So 6 times 1, we get 6. Next one, lots of minus signs to mess us up. -1 multiplied by e to the power of 1 divided by -1, which is -1 times e to the power of -1, which can be rewritten as -1 divided by e, using exponent rules. The last one's the toughest one. We have some log expression being plugged in for z. So what we'll have here is the x value, 3, times e to the power of the z value, 2 ln 2, divided by the y value, 1. Divided by 1 doesn't do anything. We have 3e to the 2 ln 2. And we can't use the cancellation law right away. We faced lots of examples that look like this in previous homework and videos, notes. And the trick is to use the cancellation law. There can't be anything in front of the log function. We need to bring the number that's in front of the log up as a power. So e to the ln of 2 to the power of 2 using that log property. And now we can use the cancellation law. So 3 times 4, we get 12 for that answer. There's plenty of different online tools that can be used to graph 3D functions if you're interested. Google has built right into the search box, it has a 3D plotting function. This is the graph, or a snapshot of the graph of x squared plus y squared. This is a snapshot of the graph of 2 divided by x minus y. So this graph, the second one, has a problem that's occurring. The function seems to be doing something weird along this line there, and that line is the line y equals x. Because what's happening there is that on the line y is equal to x, you're getting a division by 0. And you can't divide by 0, so it's not part of the domain. And the function has a vertical asymptote, or the equivalent of a vertical asymptote along that line. So the syntax, if you want to do this in Google, you just type plot. So if I have it, plot, just that, plot space x hat 2 plus y hat 2. Hat being shift 6 on a keyboard, the power symbol. And then that will give you your graph that's shown on the left-hand side. And you can rotate it, and you can zoom in, you can zoom out, you can do different things. It's neat to play with, but we're not going to be testing anything along those lines. Okay, what else can you do with functions? In addition to plugging numbers in, you can plug letters into functions. One of the things we do when we work with derivatives of functions of one variable is we talk about the difference quotient. The difference quotient being part of the process for defining the derivative. We would take the limit as h approaches 0 of the difference quotient in order to get the derivative of a function. So I want to do something similar here as a type of practice exercise. I want to calculate this difference quotient, f of x plus h, comma y, minus f of x, comma y, all divided by h for the function that's shown up above. So I'm going to plug in the different ingredients into here. This notation means we're leaving y alone, and we are replacing the x by an x plus h. So x squared becomes x plus h all squared, plus, nothing changes for y, plus x plus h times y for that third piece. So that's the first part done. That's f of x plus h comma y. Now we're going to subtract the second part of the expression, f of x comma y, so minus x squared plus y squared plus xy, and then we have this all divided by h. Okay, we'll simplify. We're going to FOIL out the first bracket. We'll get x squared plus 2xh plus h squared after you do the FOIL, plus y squared plus, and I'll distribute xy plus hy minus x squared minus y squared minus xy, all divided by h. And look what happens. Look at all the stuff that just gets destroyed. We have an x squared and a negative x squared. We have a 2xh and a negative. Oh wait, we don't have one of those. That doesn't cancel. We have a y squared and a negative y squared, and we have an xy and a negative xy, and everything else survives. So 2xh plus h squared plus hy, all divided by h. Then we can common factor an h on top, 2x plus h plus y, all over h. And then for h not equal to 0, we can cancel. If h is equal to 0, we cannot cancel. Gets rid of some information. So 2x plus h plus y. That would be your difference quotient. Now if you take the derivative of this function with respect to the x variable, which is something we're going to talk about next, how you take the derivative of a multivariable function, that derivative will be equivalent to this expression in the limit as h approaches 0. So it would be 2x plus 0 plus y. We'll see that there's shortcuts to taking the derivative of this type of an expression, just like our old derivative shortcuts are product and power and chain and quotient rules. That's much faster than doing a difference quotient. Just for the sake of argument, why didn't we do this? We did f of x plus h comma y. Why didn't we do f of x comma y plus h? Why did the x get the extra h instead of the y? And the answer is there's no reason for that. We could have done this instead. We could have looked at the difference quotient for the y variable instead of the x variable. So if we do that, we'll get the following. We'll get x squared plus, now we're replacing the y by y plus h squared plus x times y plus h minus f of xy, x squared plus y squared plus xy, all divided by h. And we cancel, well, let's FOIL first, x squared plus y squared plus 2yh plus h squared plus xy plus xh minus x squared minus y squared minus xy all over h. Now we can start canceling things. We have an x squared and x squared. We have a y squared and minus y squared. And we have an xy and a minus xy. And this looks a lot like the last one. It's almost the same story, almost the same picture. Only terms with h are going to survive. I'm going to common factor in h from the top. So 2y plus h plus x all over h. And then for h not equal to 0, we can cancel. Now we're left with 2y plus h plus x. This is in the limit as h approaches 0, this will give you the y derivative of that function up at the top. So yes, we will have x derivatives and we will have y derivatives. So we'll talk about derivatives after creating examples of multivariable functions. Some of these are extremely easy, and some of these are a little bit more challenging and require more thought. But the creation of multivariable functions would be part of the process of optimization. You want to find the max and min of something. Well, you have to have a goal in mind. What are you trying to maximize? Like, what function represents the quantity of interest that you're looking for the maximum of? So in the farmer fence example, I'll go back to that one, the simplest one. A farmer has some unknown amount of fencing material, so 160 meters, 100 meters, whatever it is, wishes to build a rectangular fence of maximum area against a straight section of river. Let x be the width of the fence and let y be the length. What function does the farmer want to maximize? So it's kind of a silly one. It's going to look silly when I show you the solution. Here's the river. I'm going to draw the fence. Here's the fence. Here's your x part, your width. Here's your y part, your length. You're looking to maximize the area enclosed. So the function that you want to maximize is the area function. A of x comma y is equal to x times y. That's it. That's the function you're looking to maximize. In the examples we saw previously, we had other information that allowed us to write y in terms of x and make this a function of only one variable. But here we don't have that information, so it's going to stay a function of two variables. And then part B, what is the value of this function at the xy coordinate 5, 10? So a of 5, 10 is 5 times 10, which is 50. And that's it. Nothing else to do. Not a trick question. Okay, next one. When there are U nights before the next Halloween and V nights before the next full moon, the number of pumpkin licenses sold that night by the pumpkin marketing board is given by that function. The price for a pumpkin license is given by that function. Part A of the question asks, what function would you maximize to find the day with the highest pumpkin license revenue made by the pumpkin marketing board? So you got to think about what is the revenue here? How much money does this marketing board make based on the price and based on the number? So if you're selling cookies and each cookie is $2 and you sell 10 cookies, what's your revenue? That's basically what this question is asking. So revenue is equal to the number sold multiplied by the price. The price for each one. So how many does it sell? It's going to sell n of u comma v. And that's multiplied by the price, p of u comma v. So I'm just going to plug that in. I'm just going to plug all this stuff in. N of u comma v, 150 minus u all squared minus 1 minus v all squared. And then I'm going to put big brackets around that. That gets multiplied by the price function, 402 divided by 1 plus u plus 10v. So what this model is telling us is let's see. When u is equal to 0, yeah, I'm not going to try and interpret it. It's just a model that we have. The number being sold is a function of how far away you are from Halloween, and then the price is also a function of how far away you are from Halloween, and these are also both functions of the time until the next full moon. So it's some very bizarre model, and this is all we have to do. Multiply the two items together to create a function that represents the total revenue. Part B is to evaluate this model at u comma v is equal to 140 comma 6. So 140 days before Halloween and 6 days before the next full moon. What is the revenue going to be from the sale of these licenses to grow pumpkins? So R of 140 comma 6 is equal to, just replacing the correct thing with the correct thing, we have 150 minus 140, which is 10 squared, minus 1 minus 6 all squared, and that's multiplied by 402 divided by 1 plus 140 plus 60. And we simplify, we have 100 minus 5, or minus negative 5 squared. Negative 5 squared is positive 25. 100 minus 25, we have a 75. And then we have 402 divided by 201, which is 75 times 2, which is 150. So they're going to make $150 selling pumpkin licenses on that day, whatever that day is. Third example is the hardest type. Requires a little bit more thinking about what does revenue mean. Waldo appears again, this time with an illegal goat petting zoo. And Waldo makes some revenue of P dollars per admission ticket and B dollars of revenue per bucket of goat food that he sells. And those are his only two sources of revenue. That's what it says. His only two sources of revenue are admissions tickets and goat food. Waldo has paid some consultants, and those consultants indicate that 140 minus B times P customers will visit per day. So if the ticket price is high and or the price of a bucket of goat food is high, he's not going to get very many customers. And on average, those customers will purchase 10 minus 2 times B buckets of goat food. And the question is, what function would you use to optimize the revenue as a function of P and B? So conceptually, when the prices of these things go up, when the admission price goes up and or the price of the goat food goes up, he's going to get fewer customers. He's going to make more money per customer, but have fewer of them. So there's got to be there's likely some middle ground of prices, B and P, that will maximize total revenue. So the function that we're after, revenue function, is equal to the sum of both types of revenue, is equal to the ticket revenue plus the food revenue. The ticket revenue is equal to the number of tickets sold times the price. I'll put number of customers times price times admission, I should say. And then the food revenue, that's going to be equal to the number of customers times buckets per customer times price per bucket. So maybe every single bucket is extremely expensive and every customer buys one on average. Maybe every bucket is cheaper and every customer will buy three on average. As you change these numbers, B and P, these two inputs into the revenue are going to change. Let's construct what the function is. This is going to be R of P comma B. So number of customers, it says 140 minus BP customers, 140 minus B times P, and then multiplied by the admission price is P. So that part's done. Plus, now the number of customers is 140 minus BP, times the number of buckets per customer. It says on average we'll purchase 10 minus 2B buckets for a given price B, and then the price per bucket is B. And that's it. That's our model. That's the function that we want to maximize in order to maximize the revenue. And the last part B, says, what is the value of this function at 10, 4? And notice in all these examples, I'm just giving like random numbers to plug in. These aren't necessarily the values of the max. So what is the revenue at this particular set of parameters? If the entry cost is $10 and one bucket of goat food costs $4, what's the revenue? We're going to have 140 minus 40, 10 times 4, times P, so times 10, plus 140 minus 40, times 10 minus 8 times 4. So we'll have 100 times 10 plus 100 times 2 times 4. So I'll have 1,000 from the first part plus 800 from the second part. $1,800 will be the revenue that's made from this illegal goat petting zoo. We'll stop here and continue with the next topic, the next video.